Today we're going to talk about how resistors behave, or electrical circuits behave, whenever you have multiple resistors in a circuit itself. So in front of you is a circuit with 3 resistors. As a reminder, the positive terminal of the battery is here, the negative terminal is here, and since we're dealing with whole flow, our current is going to flow in the direction of high voltage to low voltage. So it's going to flow around any circle like that. Okay? But overall, what is our total resistance of a circuit? Well, let's say this first resistor is 100 ohms. This resistor over here is 50 ohms. And this resistor here at the very bottom is, let's go 25 ohms. And let's say, just for kicks, our battery voltage is 17.5 volts. Okay? Well, conveniently enough, this is what's called resistors in series, right? There's no other optional course. Like a resistor, it has to go through this first resistor, the current has to go through this one, it has to go through this one, and 100% of the current has to go through the 25 ohm resistor. So 100% of the current has to go through the 100 ohm resistor, the 50 ohm resistor, and the 25 ohm resistor. So that's what happens whenever resistors are in series with one another. And when resistors are in series, they're additive. So resistors are in series. R total equals R1 plus R2 plus R3 all the way to Rn, however many resistors you have. So in this case, our R total, we have 3 resistors. That's going to be equal to 100 plus 50 plus 25. So our total resistance is equal to 175 ohms. Therefore, we can also say we can redraw this circuit as having a single resistor. So we can actually redraw this circuit like this with our battery, and this is still our 17.5 volts, and this can be 175 ohms. Therefore, we can use Ohm's law. Remember, that is V equals IR, and state that the total amount of current flowing through this system, we have 17.5 volts equals I times our total resistance of 175 ohms. So our I is equal to 17.5 over 175, which equals 0.1 amps through this circuit overall. Okay, what happens whenever you have a scenario where 100% of the current doesn't have to flow through each of the resistors? Well, how can that be? Well, a common example is like a string of Christmas lights, right? You're going to have each one tapped off of the other. So how do we actually draw that? Well, here's a 3 resistor circuit drawn like that. Okay, so you have a common, essentially a supply line and a return line. So you essentially have a supply line here and then a return line down here. This is going to be at a constant voltage here, at a constant voltage, constant. So you're going to have some of the current flowing through here, some of the current flowing through here, and some of the current flowing through here. And then whenever you get down to the bottom, you're going to have 100% of the current flowing through the battery. So you're going to have 100% here, 100% here, and some X, Y, and Z percentage through each one of these branches that if you add up X plus Y plus Z, they'll equal 100%. Okay? So this is what's known as resistors in parallel. Right, 100% of the current doesn't have to flow through each resistor. So how do we actually add up resistors in parallel? Okay, well, for resistors in parallel, it is denoted by this relationship. So you have 1 over your resistance total equals 1 over R1 plus 1 over R2 plus 1 over R3 dot 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 1 over Rn. So just for illustrative purposes, let's make each one of our resistors, let's make it an equal value. Let's make each one of our resistors 300 ohms. So let's make this one 300 ohms. Let's make this one 300 ohms. And let's make this one 300 ohms. It's pretty self-explanatory that if all these resistors are the same, then you're going to have 1/3 the current flow through here, through X, 1/3 through Y, 1/3 through Z. However, if you crank up the value of this resistance, so let's actually do something a little bit differently here just to illustrate this purpose. Let's make this one, let's make Z 600 ohms. 600 ohms for resistor Z. Okay? So intuitively, you can determine that since Z has a higher resistance, more of the current is going to flow through X and Y than Z, right? But in overall, like, what is the overall equivalent resistance to the circuit? Well, we can determine that by based on the equation that I gave you. So we're going to have 1 over our resistance total equals 1 over 300 plus 1 over 300 plus 1 over 600. So now we do not have common denominators. We must equate that to common denominator, so that'll go to 2 over 300 plus, 2 over 600, multiplied top and bottom by 2 over 2, plus 2 over 600 plus 1 over 600. So 1 over RT equals 5 over 600, which is equal to 1 over 30. Nope, wait. I can't do division in my head. Excuse me. Which is equal to 1 over 120. So therefore, our resistance total of our circuit, our equivalent resistance, is equal to 120 ohms. So once again, we can redraw this circuit. With a 120 ohm resistor and whatever our battery voltage is. And that is the total amount of current flow out of your battery here. Right? We still don't know what X, Y, and Z is. We'll cover that when we get to Kirchhoff's voltage and current laws. We'll cover that in a separate video slide. But know that the overall equivalent resistance, so your 100% current value, can be determined by V equals IR using 120 ohms as R. All right, but what about whenever you mix those two concepts together? Okay, what about if you have resistors in series and parallel? Well, how do you solve that? Well, it's the same way as before. Let's actually denote this one as a 250, a 250 ohm resistor and a 500 ohm resistor. And let's call these 100 ohms each. 100 ohms each. So how do we figure out the total overall equivalent resistance of the circuit? Well, first off, we're going to have to look at everything in parallel first. So we're going to break it apart and break it into components. You have 3 resistors in parallel here. So therefore, you're going to figure out what they are first. So 1 over RT equals 1 over 250 plus 1 over 250 plus 1 over 500 equals 2 over 2 over 500 plus 2 over 500 plus 1 over 500, which is equal to 5 over 500, which is equal to 1 over 100. Therefore, your total equivalent resistance is equal to 100 of just these three in parallel. So let's redraw this circuit as it is now. So you have your battery, a 100 ohm resistor, a 100 ohm resistor that we found from our equivalent resistances of our parallel. So right there. And another 100 ohm resistor on the bottom. And now we go back to our original one in series. Remember, they're just additive, so R1 plus R2 plus R3 all the way to Rn equals R total. So our total equivalent resistance is going to be, of this new circuit that we have drawn, is equal to 100 plus 100 plus 100, which equals 300. So we can redraw this circuit. Like so, with one 300 ohm resistor. So you're going to have 100% of your current flowing through each one of your 100 ohm resistors, and then some arbitrary amount, X, Y, and Z, flowing through each one of these resistors over here. And we'll actually calculate the amount through each one of these parallel resistors through X, Y, and Z, like I said, in a separate lecture. And that is how resistors behave in series and in parallel.